welcome to the third lesson cycle presentation for Unit 1. It's called Lego Your Hate for Math. This is juggling is sometimes called the art of controlling patterns in time and space. Now, this unit is especially important to all of you, even those of you who don't consider yourself to be interested in chemistry or physics or science in general. The ACT Science is primarily going to be testing you on your ability to make graphs, interpret graphs, and draw reasonable conclusions from data. So this is going to be really important for all of you who are interested in going to college after high school. So the first thing, you should be able to create a graph from experimentally determined data. You should be able to analyze a graph to determine the relationship between variables. And you should be able to create an equation from the graph. So what you should already know is that science requires measurement. And these measurements are often converted from grams to kilograms or meters to centimeters. And there's often a relationship between variables that are measured. So sometimes, whenever you allow a ball to roll on the floor for a longer amount of time, sometimes the distance that ball travels increases depending on the situation. Sometimes whenever you add more M&Ms to a scale, the mass goes up. So these variables are related somehow. And so the question is what is the relationship between these variables? So what you learned in the lab, you should have learned that mass and volume are related for objects of the same composition. So this composition right here, these Legos are made of the same type of plastic. So because of that, they have the same composition. So there should be a relationship between mass and volume. In fact, you should have gotten from a graph of mass and volume to be a linear relationship when you graphed it as a scatter plot. Now the scatter plot is kind of what you see here, where you could have x's and you're graphing all the data points. So whenever you do that, you're graphing all those data points. You should be able to see a generally linear relationship. So you should have also been able to take that graph and you should have been able to convert it into an equation similar from algebra. So the types of graphs you can see, there's always going to be data. There's always going to be a type of analysis that you want to do. And if you ever use like Microsoft Excel or Google Sheets or some sort of spreadsheet program, I think Apple's is not called Keynote, it's called Sheets or something like that. They will always do what you ask them to do. It is up to the user to determine what type of graph should be used. And the user shouldn't just guess and say, oh, this makes it look better. It should be based on the type of data that you have. So, for example, bar graphs. Bar graphs are usually real common in elementary school. You often see them in math classes. They're used for descriptive data. In other words, like in 1984, there were 8 red something sold. Okay. They're really good for descriptive data, for counting the number of things that occur. Okay, but they're not really good for whenever you're trying to look across a pattern of data that's continuous. So these are used for comparison, not for determining the relationship. Pie charts. Pie charts can be really useful if you're comparing data that's percentage or proportional. So in other words, I have 1,000 students. 500 students were this, 200 students were this, 220 students were this, 80 students were this. That's great for being able to display the data and show the relationship or how much more likely something is to be than another. So pie charts are particularly useful, like I said, percentage or proportional. A scatter plot is it demonstrates how the variables affect one another. So, how does your classwork score affect your assessment score? So, if your classwork scores are 90s and 100s, are your assessment scores 90s and 100s? Okay, hopefully you would see that relationship where people who don't do well on classwork aren't doing well on the test because they're not understanding the concepts. So, you're looking for the variables to see if they're correlated or if there's a pattern. Scatter plots are by far the most common graph that we will use in chemistry or physics. Okay, 99% of the graphs that you see are going to be that. Like you may see a bar graph with energy, you may see a pie chart occasionally, but 99% of the time, when we're looking for a graph, it's going to be a scatter plot, especially in the lab. So, it says, what type of graph would you use for the data below? You have time spent studying and you have course grade, and this is a continuous variable. So I'm adding more time, I'm adding more time, I'm adding more time. It's not like saying, hey, if you did a bar chart or bar graph here, it wouldn't be particularly useful. You're looking to see if you spend more time studying, does your course grade increase? And a lot of people say, well, no, because if I study for 10 minutes, I got a lower grade. Remember, whenever you have a scatter plot, the data may have weird points, but may overall go in the upward direction. So you need to look at the data as a whole. So the best plot for this would be a scatter plot. Next, it says, does the graph fit the data, or does the graph fit the data? And then to explain yourself. In this case, you says time use on an average weekday for a full-time university student and college student. Okay, because of this, there is a specific amount of time that everybody's comparing. Everybody has 24 hours in one day. So because of that, we're looking at these things in terms of almost a percentage. So you're able to say, okay, well, what does the average college student do? Where do they spend their time? And so this is a comparison value with a set number or total. So when you're looking at the percentages, it makes a lot of sense to display this in this way. And what you can see is, a lot of the biggest chunk other than sleeping is leisure and sports. So because of that, it's an interesting thing to say, well, why are people not doing as well in their studies as maybe they should be? If you were to look in an average day, they're spending 3.3 hours a day in school compared to in high school or middle school, elementary school, they're spending 9 hours a day, 8 to 9 hours a day. So it's one of those things that you can look at, and with the freedom of a university or a college schedule, you also have to be disciplined enough to say, okay, well, what do I need to spend my time on? Is there a relationship between the two variables? Can you make predictions based on the graph? So if you look right here, this is a pretty interesting scatter plot because there's a lot of data. It would be difficult for you to make a reasonable um, determination as a predictor because I mean it looks like the data kind of goes like that, but you have a lot of variables below and above, so this line doesn't really valid. So because of this, I would say that these variables aren't particularly related to one another, so you can't use one to predict the other. Now, when we construct a graph, it's really important that you use a set structure whenever you're doing this to make sure that you get all the important parts of a graph. The first thing that you have to do is you have to identify the variables. What did you change in an experiment? What has changed in a situation? What stays the same? You need to title the graph. You need to scale the graph. You need to plot the points. You need to get the line of best fit, calculate and analyze the relationship. These are all things you're expected to do whenever you construct a graph, and you will be graded based on this because these are all really, really important to whenever you're graphing data. So the first thing is you need to be able to identify the variables. So the independent variable is the one that you have direct control over, whereas the dependent variable depends on what you change. So for example, if I'm looking at GPA and hours of sleep, I can't change your GPA and say, okay, now you have a 4.0 GPA. How many hours of sleep did you sleep last night? It doesn't make any sense. So instead, you say, well, if I sleep for 8 hours a night, does that affect my grades as I continue to sleep 8 hours a night? And that's a reasonable question. So because of that, the hours of sleep is our independent variable. It's something we have direct control over, and GPA may or may not depend on that. So that's one of those things that there's not always a relationship between the two variables. Next, you need to title the graph. And I know this seems silly, but most people forget to title the graph, and it's a very specific way to title a graph. It should be the dependent variable versus the independent variable. So it should be something like GPA versus hours of sleep for such and such investigation, for a sleep investigation, or something like that. Um, Next, you have to scale the graph. And this is the one that causes the most problems because you want to make sure that you use the entire available graphing area. If you have a graph and it fits like this, it's really hard to visualize any sort of relationship between the variables because all your data is squished together. So instead, what you want to do is you want to make sure you use the whole graph by taking the maximum and minimum measurements for each value. So something like 0 hours of sleep and like 12 hours of sleep. And then you want to divide those up so that each box represents a specific value. Okay. So that means that each line here, each division could represent maybe, I don't know, half an hour. Okay. And if it represents half an hour, does that mean that your GPA has to represent half a point? And that wouldn't make any sense because on a 4.0 scale, that would only get you up to like right here. So you want to use the whole graph on both axes. So this is done independent for each variable. So for example, if I have 12 hours of sleep as my maximum value, I'd say 12 minus 0, and then I would divide by the 20 boxes that are there. Now, when you do that, you get 12 divided by 20, which is not a real nice number. So you may have to round it a little bit to make it a nice number for you to work with. But if you had 4.0 minus 0.0, which is the lowest grade you can get, you get this. Each box would be 0.05, and that's a nice number because it goes 0.05, 0.1, 0.15, and so on and so on and so on. But if you were to do something like 12 divided by 20, it's going to be a messy decimal. So you want to make sure you work primarily in ones, twos, fives, tens, those sorts of things. So it can be like 1, 2, 3, 4, 5. It can be 2, 4, 6, 8. It can be 0.5, 1, 1.5, etc. You want to work in zeros, ones, twos, and fives. So next you plot the points, and when you plot the points, that's putting all the data on the graph. Now, one thing that people do is they forget their scale. Okay, remember you scaled this thing out where this was 12 and this was 0, but then people will go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and they'll mark this as 12. Well, remember, you defined your scale here already. So make sure you use the scale that you made to properly graph the data. Now, once you have your data, people have a tendency to connect the points. Okay, they have a tendency to go, okay, connect, 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 connect. We don't do that. Okay, we're not going to connect the points in this class. Instead, what we're going to do is we draw what's a line of best fit. So you're taking the average of all these data points together. Okay, now you are not going to go through all the points, but you are trying to go through as many points as you can. Okay, whenever you do that, you are going to have some points above the line, you're going to have some points below the line, but they should equal out. Now remember, when you do this, this has to be a smooth, continuous line or curve. It can be a straight line. It can be a straight line. It can be a straight line. Or it can be a curve. A curve. Something along those lines. It's the one that best matches the data. Now, if you have a linear line, okay, I know that makes no sense really, but you have a linear line, you can find the slope of that line, and that's usually the next step, is to find the slope. So what's the rise, what's the run? Your slope, your point slope formula, where you do y2 minus y1 over x2 minus x1 from math. That right there is your slope. You need to be able to do that. And then finally, um, you need to be able to find the meaning of the slope. So what is the purpose of the slope? You don't just calculate the slope because you want to calculate the slope like you do in a math class. The slope has to have meaning. So in our example that we gave you, it says GPA divided by the number of hours of sleep. So you have a rate, and it says, well, if you sleep more, you generally have a higher GPA. And then you can talk about the reason why you have this relationship. Okay, if you were to graph a distance versus time graph, that right there is your speed, and that means something. Like we're saying, you have a high speed, a low speed, you'll get there faster, you're going to get a speeding ticket, those sorts of things. So there has to have a reason for calculating the slope. And then finally, you would look and you would analyze the graph. Okay, what does the data actually say? Now, whenever you analyze the graph, there's two real. The ultimate reason for having this graph is to be able to predict untested data points. And so, whenever you have this graph, you can actually test through interpolation or extrapolation. Okay, inter means between. So, whenever I say I'm going to interpolate data, see how all my data points are right here in this little section of the graph? If I wanted to test right here, and I didn't have a data point that matched that exact value of x, I could use the graph to make a prediction. Because I'm making a prediction between tested data points, that's considered to be an interpolation. An extrapolation is either before all the data points that you tested or after all the data points you tested, and you see that here. It is very, very careful, or it is very, very important that you be careful when you extrapolate. Extrapolations do not, these relationships don't always continue forever. Okay, so here's an example. It says this is the impact of family income on IQ. So this is making a prediction that if your family makes a certain amount of money, you are more likely to have a higher IQ. Incidentally, that's one of the reasons why people don't think that IQ is a measurement of intelligence. But you can expect this relationship to continue on forever, to the point where you have Mark Zuckerberg's kid who's going to have an IQ of like 5,000. Okay, for a couple of reasons. Well, it doesn't go up that high, number one. And number two, it's not going to be a linear relationship forever. So you have to be real careful whenever you decide to extrapolate because most relationships will actually curve off. This likewise is another example. It's a Beer's plot. So if you were to take something and shine a light through a solution, some of that light would get through, depending on a lot of other factors. But the main one being concentration. And we'll talk more about this later, but whenever you shine this in, you're not going to keep saying, okay, if I put more stuff in here and more stuff in here and more stuff and more stuff, I'm going to get less light. Well, there becomes a point where you don't have any more light to get through. So you're going to have a curve off in this relationship. And you actually see this here. If you were to look at this graph only at this particular point right here, it looks very, very linear. But once you go out further, you realize, okay, well, it actually curves. So you have to be real careful when you extrapolate. It's much, much better if you interpolate than extrapolate. So it says create an appropriate graph given the data below. So if you were to look at this particular data, you'd have to say, okay, well, what is the most reasonable graph for me to be able to take at this point? And it says, well, you've got a total number of people, and because you have a total number of people, the best bet would be a pie chart because you're comparing a total. So if you were to make a pie chart, you could say, this is soccer, and you could say tennis, gymnastics, swimming, and track. If you were to look at the pieces, the best way to do this would be with Excel software. But if you were to look at just kind of freehanding it, you'd have something that looks like this. By far, the biggest piece of this is going to be soccer. Okay, the next biggest piece is going to be swimming, and then the next biggest piece is going to be swimming, and then the next biggest piece is going to be track. Okay, and then the next biggest piece is going to be, we'll put track there, and then you're going to go down from there to gymnastics and tennis. And the reason why I decided to use this pie chart is because I have a set total number and I'm looking to compare. It's not like I say, well, if I increase the soccer, does the number of people, it doesn't work that way. This is purely a descriptive or comparative relationship. So the next one, it says create an appropriate graph given the data below. In this case, it says you've got pH and you've got average plant growth. Okay, so you could look at this in one of two ways. You could look at it as a linear relationship, and you want to know if I increase the pH, does the average plant height go up? And you could absolutely do that. Okay, or you could do this one as a pie chart, depending on the method of analysis you're trying to do. But in this case, I don't have enough information, so I've got to go with what I think the experiment's going to be. So at this point, you decide whether you want to make it a bar graph or a line graph, and then you'd be ready to defend your choice whenever you come into class. Okay, the next one, it says determine the slope, if any, of the data below. Does the slope have meaning? So in order for me to be able to find the slope, the first thing that I need to be able to do is I need to be able to graph the data. In order to graph the data, okay, you look at it and you say, okay, I've got mass of liquid and I've got volume of liquid. So what I'm going to do is I'm going to say that I directly control the volume, just like in the lab. And I'm going to measure the mass of the liquid and see if that changes as a result. Okay, now you should be able to do much better because you can have some time to actually draw this out. But if you were to look at this relationship, okay, you've got 2. So I'm going to say that this is 2, 4, 6, 8, 10, 12, and then it's going to go all the way to 20. So 14, 16, 18, 20. Now if you were to look at the plant growth or the mass has to go all the way up to 100. So I'm going to do it by sections of 10. So 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. So then I would plot my points and I would say, okay, I've got 4 and 20. I've got 20 and 100. I've got 15, which would be right here. And I've got 75, which would be right here. And I've got 8 and 40. And that's it. And if you look, you have a pretty reasonable straight line. So because you have a pretty reasonable straight line, you can calculate the slope. So the best way to do the slope is directly from the line. So since I have a straight line, I'm just going to pick 2 points on the line. And I'm going to say that my slope is going to be 20 minus 10 because I picked this point and this point. and I do 20 minus 10 divided by 4 minus 2, and that gives me a slope of 10 over 2, or 5. Now the meaning of that slope is 5 grams per centimeter cubed, which you should recognize from your lab represents the density.